So in this video we are looking at the idea of an inverse function. So if a function f is 1 to 1, then it has an inverse function. Okay, we'll come back to that because it's possible for something to have a function if it's not 1 to 1. It's just that that inverse won't, it's possible for something to have an inverse if it isn't 1 to 1. It's just that that inverse won't be a function if the original function isn't 1 to 1. Notation, the inverse function of f is denoted by f to the power of -1, and we've actually seen this notation in trig, right back from year 9. The opposite of, if y equals sine of x, then x equals inverse sine of y, and we use that sine to the power of -1. It should be really clear that that power of -1 in this instance is purely being used to indicate an inverse function. It doesn't mean we know that x to the power of -1 is 1 on x. We know what negative powers mean. This is not a negative power. This is just a way to denote inverse function. And to that end, it's actually quite a confusing notation. So an inverse function performs the opposite operations in the reverse order. So, what we've seen here is we're essentially saying that if f of x is sine of x, then the inverse function of that is inverse sine of x. And the idea is that they do the opposite operation, so they sort of undo each other. So for example, if we were to substitute the inverse function into the original function, and have sine of inverse sine of x, or if we were to substitute the original function into the inverse function and have inverse sine of x, both of those things would just give us x. So the point being that the sine and the inverse sine undo each other, and we just get left with x. It's the same logic of saying, if we've got a function, let's say it's 2x, then its inverse function would be x divided by 2. It's the opposite operations. And to that end, then, if we're going to substitute the inverse function into the original function, so that is, meaning that we get 2 times x on 2, we just get left with x. And the same would be true if we did it in reverse. If we were to substitute the original function into the inverse and hence get 2x over 2, we get x. Okay, so we're essentially creating a function that does the opposite operation, the inverse operations in the reverse order, and so therefore if we were to sub one of those functions into the other, those operations all end up undoing each other and we just get back to x, which is essentially what this line is saying here. This line also has a graphical interpretation. We'll come to that in a minute. So yes, I've listed out some further examples there. So for example, if f of x is x cubed, its inverse function, f to the -1 of x, is the cube root of x. And that is true because that if I were to take the cube root of x and substitute it into the original function, hence getting cube root of x all cubed, or if I was to take x cubed and sub it into the inverse function, hence getting cube root of x cubed, we end up with x. If f of x was x plus 5, then its inverse function would be x minus 5. And that's going to be true because if I take x minus 5 and sub it into the original function, I get x minus 5 plus 5, and hence I just get x. Similarly, if I were to take x plus 5, the original function, and sub it into the inverse function, x plus 5 minus 5, I also get x. Okay, there are two different functions where the operations undo each other. And we could extend that if f of x is 2x plus 1, then its inverse function is, that should be is, not if, is inverse f of x is x minus 1 on 2. And again, if I take the inverse function and substitute it into the original function, I get this. If I were to take the original function, the original function 2x plus 1 and substitute it into the inverse function, I get this, and those two things both simplify to give me x. Okay, so to obtain the rule of an inverse function, we have to be a bit particular about what we write here, because the key is that we have to be really careful not to write something that's mathematically incorrect, which is very easy to do in this process. Okay, so it's really important that you're writing down the right things and that you don't just skip the steps. So the key ones, the first one's probably a little bit trivial and it'll depend on the format that your function is given. But we're probably going to introduce y into the problem. We're going to let y equal f of x. Okay. Then in step 2, we're going to swap x and y to find our inverse function. Okay. And so another way we could write that would be to say, if we've got our original function in function notation, would be to write f of y is equal to x. Okay. It's important, it's really important that you don't have, that there's a clear delineation between the first line and the second line. For example, if you have the original function is y equals 2x plus 5, the next line of working after that cannot just be x equals 2y plus 5. Okay? These are not equivalent equations. There's no algebraic sense in how you got from here to here. Okay? If you're going to write this, you need to write a line in between which says that you're going to swap x and y for the inverse function. Okay? It is really important that your mathematics doesn't go directly from this line into this line without something being said in between. Okay? That's really key. So introduce y to your problem, swap x and y, then we're going to solve for y, and then we're going to answer the question. This is the place where most of you will lose too many marks because you don't then go on and answer the question, which means inverse f of x equals something. And you should usually give the domain. So the domain of the inverse equals something. Okay. Usually the question will specify rule and domain, but you'll remember earlier in this topic we talked about the fact that a function is only fully defined if its domain is given, and quite often with these functions there's restrictions involved in order to make sure that the inverse exists, and therefore if you don't give the domain, the implied domain is assumed and it's not correct. Okay, so please get in the habit of giving your inverse function and not just y equals f to the negative 1 of x equals, or g to the negative 1 of x if your original function was g of x, and giving the domain of that inverse. Now, the key thing that happens here, which has all sorts of implications, is that in the process of calculating the inverse function, we swap the x and y position in the equation. Okay, so what that means is that everything that's to do with x in the original function now becomes to do with y in the inverse function, and vice versa. And so that means that the domain of the inverse function is equal to the range of the original function. Okay, and it means that the range of the inverse function is equal to the domain of the original function. Okay, so your domains and ranges switch around. Can you be clear? Can we please be clear here? I've just marked some Year 12 tests where there's a lot of issue around people just writing domain and domain equals range equals. In a problem where you've got an inverse function, you have two different domains and two different ranges. Domain of the original, domain of the inverse, range of the original, range of the inverse. Please be clear about whether you are talking about domain of f or domain of f to the negative 1. Don't just write domain equals. You've got more than one function. Which domain are you talking about? Okay. Okay, so like any function, an inverse function is only fully defined if its domain is given. So I referred to this just before. If its domain is given. Obviously, if its domain is the implied domain, you don't technically need to give it because we would then assume that. But as I said, often the domain here won't be the implied domain. Now, graphically, I want to talk about this a bit. Graphically, the inverse function is, so what happens here is, remembering we're swapping x and y. So let's just draw ourselves, an axis here. All right, let's say I've got the point 1, 2. When I swap the x and y coordinates of that point, it becomes the point 2, 1. All right, let's say I've got the point, so I've gone 1, 2, just trying to keep a sort of square scale here. We'll put that point a little high and move it down a bit. Okay, so let's say we've got the point negative 1, negative 1. We swap its x and y coordinates, it stays at negative 1, negative 1. Okay, let's say we've got the point 2, negative 3. when we swap its x and y coordinates, it goes to be at negative 3, 2. Now what's actually happening when we're swapping x and y values is we are reflecting these points in the line y equals x. Okay, so this point here at 1, 2 went to this point here at 2, 1, reflected in the line y equals x. The point negative 1, negative 1 didn't go anywhere because it's on the line y equals x. Okay, the point 2, negative 3 became the point negative 3, 2, reflected in the line y equals x. Okay, so graphically what happens is the graph gets reflected in, every point gets reflected in the line y equals x, and so the whole graph shape is a reflection. Graphically, the inverse is a reflection in the line y equals x. Okay. Now, I want to go back to the statement that was made right at the beginning of this section, which says, if a function is one-to-one, then it has an inverse function. Okay, so let's be clear about something. Let's say, just draw over here for a second, let's say I had the parabola, y equals x squared. Y equals x squared. Okay. Now, if I take the inverse of that, reflect it in the line y equals x, swap all the x and y, take all the points and swap all their x and y coordinates, the graph that I get is this. Okay. It's a sideways parabola. So the top half of it is the positive square root of x, the bottom half of it is the negative square root of x. The whole thing is y equals plus minus root x, which we would normally write as y squared equals x. Okay. Now, what you'll notice here is that the inverse y squared equals x is not a function. It fails the vertical line test. And that will be true if the original function fails the horizontal line test. If the original function fails the horizontal line test, i.e. if it is not a one-to-one function, then its inverse will fail the vertical line test and not be a function. Okay, so therefore, in order for a function to have an inverse function, we need to only be looking at, just make my pen a bit wider here, we need to only be looking at a one-to-one function to start with. Okay, so if we started just with that half of the parabola, which is a one-to-one function, then we would get the positive square root as the inverse function, and it would also be a function. Okay, if instead we had started with the left-hand side of the parabola, also a one-to-one function, okay, when we mirror that in the line y equals x, we get the bottom half of the parabola. Okay, and so that's really important too to think about later on. So the whole idea is your original, if your inverse is to be a function, i.e. pass the vertical line test, then the original function needs to be a one-to-one function. It needs to pass the horizontal line test so that when you mirror it, what you end up with is a function. Okay, you can also think about it as sort of x and y values. So you know that something that is many to one, there is more than one point with the same y value. So you know you might have this point at 2y and this point is at negative 2, same y value, which means your inverse function will go through y2 and y negative 2, and therefore fails the fact that you've got 2 points with the same x coordinate, which is the definition of a function. You can't have 2 points with the same x coordinate. So if your original function has 2 points with the same y coordinate, your inverse function will have 2 points with the same x coordinate and therefore not actually be a function. Okay, so needs to be one-to-one to start with. The process, we swap x and y, we solve for y, we make sure we answer the question, we give the domain. Graphically what we're seeing here is a reflection in the line y equals x. In terms of your CAS, I haven't got my CAS open here, but this box covers everything needed. There is no magical instruction to tell your CAS to find an inverse function. you can tell your CAS to do the maths that's needed. So you could define your function and get it to solve f of y equals x for y, which would be swapping x and y and solving for y, and then answer the question from there. But in all honesty, most of the functions you're dealing with here, the time taken to type that in is, you could have solved that for y more efficiently than you typed it in. So I wouldn't say that you need your CAS very often for inverse functions. Okay, let's work through some examples. So we've got the function f of x equals 1 minus 4x. It's a linear function, which is all linear functions are 1 to 1, so there's no issue there. Find the inverse function, f to the negative 1, and sketch the graphs of y equals f of x and y equals f to the negative 1 of x on the same set of axes. Okay, so we're going to, just let me reduce the thickness of my pen again. Okay, so we're going to let y equal 1 minus 4x, okay, and then we are going to swap x and y for the inverse function, and we do need to write that, or a sentence to that effect, in between those two lines of algebra, because those two lines of algebra are not equivalent. They are not equivalent equations. The maths of, well, hang on, what did you do to both sides of the equation to get from that first line to that second line? You didn't do any correct algebra, you made a manual swap of x and y, and so you need to note that. Okay, now we're going to solve this for y. And in doing that, the process of doing this is how we generate all the inverse operations. If we want to generate the inverse operations, undo the things that are happening to x in the original function, we can do that by, doing the inverse operations to both sides of the equation. And so that's what we're doing. So if we subtract 1 from both sides, that's therefore the opposite of adding 1, which is what's happening in the original function. If we then divide both sides by negative 4, that's therefore the opposite of multiplying by negative 4, which is what's happening in the original function. And so this process of swapping x and y and then rearranging to make y the subject is how we're generating all those inverse operations. Okay, so we then want to answer the question, which means that we state, okay, so be clear, the question says find the inverse function f to the negative 1, and so therefore your answer needs to say f to the negative 1 of x equals x minus 1 over negative 4. Now obviously that could also be written as 1 minus x over positive 4, okay? So that would be perfectly fine as well. We should state the domain whether it's asked for or not, but actually in this case, apologies if you can hear that background noise, my dishwasher's just emptying. If you can, in this case the domain and range of f, so domain of f is R, it's a linear function, range of f is also R, which means the domain of the inverse will be R, and so that's the implied domain of that linear function anyway. So it wouldn't matter if we didn't write this in this instance. However, if it was a restricted domain, it would be an issue to omit it, even if the question hadn't specified that you needed to give it. Okay, so we've got our function and its inverse, and we want to sketch the graphs on the same set of axes. Now, I would say to you that you shouldn't be thinking at all about sketching this equation, your inverse function. You simply sketch your original function and then graphically reflect that in the line y equals x. Okay, and we'll talk about how to do that. And then that means that you're not also relying on, in case you got your inverse function wrong, you're not relying on actually sketching that graph. You're relying only on the information provided in the question, which was your original function up here. Okay, so it's really important when you're drawing, my original function is a linear function with a y-intercept at 1 and a gradient of negative 4. It's really important when you draw inverse functions and original functions on the same axes that you, I'm just making sure I get these in the right place. I think it will be fine to put my axes down here. That you use a square scale. Otherwise it's going to be really hard to get that mirror image happening in y equals x. It won't assist you because your graph will be skewed. So if you're going to make your x-axis, scaled as, I'm going to use quite a big scale here because I've got, in fact I'm just going to make that 1. But you want to use that same distance on your y-axis as 1, okay? So this is going to be, half, 3/4, 1/4, half, 1/4, 3/4. Okay, so you want to use the same scale so that if you were to rule in your line y equals x, it would pretty much be at a 45-degree angle, okay, not skewed. And I would strongly advise you actually draw in the line y equals x, rule it in with a pencil, to help you with these graphs. Okay, so let's draw in our original graph. So as I said, y-intercept at 1, gradient is -4. If you calculate the x-intercept, you'll find it's 1/4, which is why I used such a big scale, or such a small scale, I guess. And so I'm going to go draw a straight line. Now, apologies, it is hard to be perfectly straight on the slippery screen, but I'll do my best. Okay, so I've got a y-intercept at 0, 1, and an x-intercept at 1/4, 0. Actually, I'm just going to put that down under here. Okay, so now I wouldn't bother if I'm trying to draw the inverse function. Just let me make that pen a bit thinner. If I'm trying to draw the inverse function, I wouldn't be bothering to draw this equation. I would be simply mirroring my green graph in the line y equals x, which is about swapping your x and y coordinates. So if my inverse function goes through the point 0, sorry, my original function goes through the point 0, 1, my inverse function goes through the point 1, 0. Okay. If my original function goes through the point 1/4, 0, my inverse function goes through the point 0, 1/4. Okay, straight line, only need 2 points to draw a straight line. Okay, and so there's my inverse function. The other thing that should happen is that your inverse function and your original function should cross on the line y equals x. Okay, because that's that whole, if you substitute, let me just write on the rules. So this one is x minus 1 on -4, and this is y equals 1 minus 4x. So that comes back to that whole idea, if you were to take your original function and sub it into your inverse function, or vice versa, you get x. And that is essentially telling you that the two graphs are intersecting on the line y equals x. There are instances where inverse functions can intersect at points other than y equals x, but it's fairly rare, and once you draw your graph, you'll be able to see that and calculate them separately. Part B actually asks us to find the coordinates of the point where the original equals the inverse, so we're being asked to find the coordinates of that point of intersection. Now, the key thing that I want you to note here is that the point of intersection is when, so let me write them as f of x and inverse f of x. And this one is... so actually there are 3 lines intersecting at that purple intersection point, which is what we want to find. F of x and inverse f of x, so we could solve them equal to each other to find that point of intersection, but also y equals x. So there are actually 3 different equations that we could solve here to find the coordinates of the point. We could solve f of x equals inverse f of x, which would be 1 minus 4x equals x minus 1 over -4. Or we could solve f of x equals x, 1 minus 4x equals x, okay? Or we could solve, or we could solve the inverse equals x, which would be x minus 1 over -4 equals x, okay? In almost all instances, I would go for this choice, f of x equals x, for a number of reasons. It's usually a simpler equation. Solving the original function equal to its inverse will always be a very complicated equation. And the second thing is it doesn't rely on any calculation that I've made. I was given f of x, make that equal to x, okay? So it doesn't, I'm not going to create any consequential errors by using my own inverse function, which perhaps I calculated incorrectly, okay? So I'm always going to go for solving the function equal to x, provided that the intersection point is on the line y equals x, and I can see that it is from my graph. And so I'm going to solve this one, which simply means adding 4x to both sides and then dividing by 5. So x is 1/5. The other easy thing is we're then going to need to sub our x value back into one of the equations. This is clearly the easiest equation because y equals x. They intersect on the line y equals x, and so therefore that implies that y is also 1/5, and that intersection point is at 1/5, 1/5. Okay, so here on my graph, this point is 1/5. Okay, let's have a look at another example. Consider the function g. Its domain is from -infinity to 0, inclusive of 0. And the rule is 4x squared plus 3. Okay, so that's a parabola dilated from the x-axis and translated up by 3. So essentially, it looks like that, except we're only looking at that domain, and so it only looks like -infinity up to 0, including 0. It's only that red section. Okay, that's going to be really important. So first of all, there is that domain restriction so that it's a one-to-one function, so that there will be an inverse function, okay? Otherwise it would be an inverse relation, not an inverse function. So that's why there's the domain restriction, but it does also have an implication for what's going to happen down the track. Okay, this time another way that I could write out the beginnings of this problem is I could simply let g of y equals x, and that's doing my first two steps at once. So I've both introduced y into the problem where there wasn't a y, and I've immediately swapped x and y straight away. Okay, so I'm not algebraically writing anything incorrect here because I'm straight away going, I haven't written the line, I haven't written the line, y equals 4x squared plus 3 and then followed it with x equals 4y squared plus 3. I've just gone straight to this point where I've let g of y equal x, and now we're going to solve this for y. So we're going to take away 3. We're going to divide by 4. And then we're going to take the square root. And when we take a square root, we get positive and negative square root of x minus 3 on 4. This is where then we get to that point where we must answer the question. So you should not be ignoring the plus minus square root in the algebraic rearrangement of this. And that's because what it's actually calculating here is the inverse would be without any restriction, the inverse without any restriction would be this sideways parabola out here, okay? But we didn't start with the whole parabola, we only started with the left-hand side of it. And when we reflect that red section in the line y equals x, we're going to get the bottom half of the parabola. So if you start with the left-hand side of the parabola, its mirror image will be the bottom half of the square root, okay? So the negative square root. If we had started with the right-hand side of the parabola, so if the domain restriction had instead been 0 to infinity, then we would be keeping the top half of the square root, the positive square root, okay? So we are thinking about our domain and things, and therefore our inverse of g is the negative square root of x minus 3 on 4. We should give the domain of g, okay, of inverse g, which is the range of original g, and looking at my graph I've drawn up there, that's that up by 3, the range is from 3 to infinity, and so that therefore becomes the domain of my inverse function. Sketch the graphs of g and inverse g on the same axis. So I've got a rough sketch happening up there. Starts at 0, 3 or 3, 0, the two separate functions, and then the direction. Obviously we're going to need to put another point if we're drawing a proper sketch, because otherwise we're not showing that it's 4x squared rather than just x squared plus 3. So we're certainly going to need a point. So perhaps, when x equals -1, it'd be 7. Okay. And so therefore this graph goes through the point 7, -1. So we definitely put those on our graph. Okay, so let's get some axes happening then. So we want to go up to 7 on the y-axis and up to 7 on the x-axis. So 1, 2, 3, 4, 5, 6, 7. Again, you want to keep things nice and square. 2, 3, 4, 5, 6, 7. Don't need to perfectly measure it, but the idea is that 1 unit on your x-axis should be about the same as 1 unit on your y-axis, because that will help you to be able to see the reflection in the line y equals x, because your line y equals x now is going to be a nice, perfect 45-degree angle if you have used a square scale. Okay, so my original function, y-intercept, is at 0, 3, that's an included point. The next point is at negative 1, 7. And it is a parabola, so make sure I actually get a turning point happening at 0, 3. And then so that's y equals g of x. And then my inverse function starts with an included point at 3, 0. And it's a parabola, so make sure you've got a turning point. Seeing too many of these sort of things happening, that's a turning point there. So make sure your graph actually turns there. Oh, sorry. And then we're going through the point 7, negative 1 for my inverse function. So sketch the graphs on the same axes. All done. Okay, third and final example here. Again, we've got a function. This is again a quadratic function. It again has a domain restriction. One would assume to make it a one-to-one function. We'll have a look at that in a second. We want to find the inverse function and state its domain and range. Okay, so let's think about our original function. So we've got y equals x squared plus 4x. So that is a happy parabola with intercepts at 0 and 4. Okay, so that essentially is that, but we only want negative 2 to infinity, so negative 2, sorry, my intercepts won't be 0 and 4, they'll be 0 and negative 4, my apologies. So happy parabola, intercepts at negative 4 and 0, and so therefore negative 2 is going to be where your x, the x coordinate of the turning point is going to be, and that's an included point, and we're only looking at domain from there to infinity, so just the right hand half of the parabola this time. So in our inverse function, when we take the square root, we get plus minus square root. In determining which is actually the rule for the inverse function, we're going to want the positive square root in this instance. Okay. All right, yeah, because our graph will essentially have, the inverse will be something like that. No, it's not quite in the right place, but anyway, we'll work it out. Okay, so it's important to think about that graph so you can think about which half of the shape you've got and therefore which half of the inverse you're going to need. Okay, so we're going to be letting y equals f of x and swapping x and y. So again, I can do that in one step by writing f of y equals x, okay, which would be y squared plus 4y equals x. Okay, so algebraically we now have a challenge here because we're trying to make y the subject, but we have y in two places in this equation that aren't like terms that we can't collect together. So what we want to think about is that this is a quadratic function, and while we know that we can have quadratic functions, written as x squared plus, bx plus c, we also know we can write them in turning point form. And the advantage of writing them in turning point form is that there's only one unknown that we can then rearrange and solve for. And so that's going to be a much more helpful form here. So I want to complete the square on the left hand side here so that I can write it in turning point form. Okay. So I'm going to add in halve and square 4 is 4. I'll take away 4 as well. Okay. And so there's the perfect square. That is y plus 2 all squared, take away 4 equals x. So by completing the square, A, we can now see that this turning point is at negative 2, negative 4. Okay. And B, we can also see that now we can also rearrange to make y the subject. Okay. We've just got the one y, so we can simply do the same thing to both sides until we get y on its own. So we get y plus 2 all squared equals x plus 4. Therefore we get, y plus 2 equals positive or negative square root of x plus 4. Don't reject one of those yet. We're not talking about inverse f of x at this point. We're just talking about y. We'll make that decision when we actually do that final step of answering our question. Okay, so subtracting 2. And so those two parabolas, now let's just be clear about, and I probably haven't used a very square scale here, but in my other, if I were to try and draw the inverse function here, its turning point would be at negative 4, negative 2, so that would be there, and it would also be going through the origin, so it's sort of going to be that, and there's the line y equals x happening in there. So as you see, because I haven't got a square scale there, this y scale is smaller than the x scale. It means that it's hard for me to actually draw that reflection in and to get those graph shapes looking correct. So it makes life much easier if when you're trying to draw the graph and its inverse on the same axis, that you use the same scale on the x-axis as you use on the y. Okay, anyway, we've made that decision. We want the positive square root. It is inverse f of x. Okay, so therefore, the inverse of f is negative 2 plus the square root of x plus 4. Can't be both of them, that's not a function. And we were also asked to give the domain and range. So again, let's be clear about, don't just write domain or dom. Domain of what? F or inverse f, okay? So domain of the inverse, we know is the range of the original. And in this case, the range of the original, the range of the purple function on the graph I've drawn there, would be from negative 4, which is the y value of the turning point, up to infinity. The range of my inverse function is the domain of my original function, which were given in the question, which goes from negative 2 up to infinity. Okay, so function, domain, and range, all three asked for. You can't have y equals, you need f to the negative 1 equals. The work today is from exercise 5G.